So we've been dealing with these things called functions. We've been describing what they are, defining them, a few of their useful properties, and we've been converting them into tables. Now we ultimately are doing this because we want to graph the function. That's the end game. We want to get a visual representation of what the function looks like, so we can see things such as the trend of the function and a few other pieces of very useful information. So what we're going to do in this section is we're going to be given a certain table of values of a function, and we want to take that table and use it to graph the underlying function. So let's say we're given the following table. So x is our independent variable, f of x is our dependent variable. It's the function evaluated at a given value for x. So let's define our domain as -1, 0, 1, and 2. And our range of f of x is respectively -1, 0, 1, and 2. Now we should tell just right off the bat by now that this is indeed a linear equation, and it's very simple, but we just want to get an idea of the usefulness of having a table when it comes to graphing a function. So just a rough sketch, we're going to sketch what this function looks like. So we have our x-axis and our f of x-axis. The f of x-axis was previously known as the y-axis, but we made that transition from the notation y to f of x, which is functional notation. We did that a few sections ago, I believe. So we should be pretty familiar with it by now. So when we have a table of values, there's a few things that we can pick out that are useful. And one of those is these are points. The point x and f of x these are points on the function line. So we have -1 and -1. That's a point on our function. We also know that 0, 0 is another point, also called the origin. We have 1, 1 and 2, 2. So once we plot, this is supposed to be a 2 actually. So once we plot these points, we can just simply draw a straight line through them. Now, we're actually going to go ahead and assume that the function is indeed continuous, continuous meaning the set of all real numbers, and continues indefinitely in both directions. If it's not continuous, we'd have breaks in it, but we're not dealing with anything like that right now. We're just getting a good handle on graphing a function using the table. So let's do a few more of these. That's actually all there is to it. Let's take a look. We're given the table of values. Our x values are -2, -1, 0, 1, and let's include 2. Then our range, our f of x, our function evaluated at each point, are respectively 2, 1, 0, 1, and 2. Okay, so we have a table of values here, and we want to just make a quick sketch of what this function looks like. So we have our f of x axis, our x axis, and from the table of values we can actually pick out the points that are on this function. And after that, all we have left to do is connect the points, and if we assume it's continuous, we just put arrows on the end of it to show that it goes infinitely in both directions. Okay, so the first point we have is -2 and 2. So -2 and 2 is right here. -1 and 1 is right here. The function, the origin is contained in the function. We also have the point 1, 1 and the point 2, 2. Okay, so the function is going to look something like this. Let's get a different color. It's going to come down like this, going to meet at the origin, and it's going to pop back up like this. So it's actually a pretty interesting looking function. And this is actually known as, it's kind of an important function. It's called the absolute value. This is what absolute value looks like, the function of it. So it continues infinitely in both directions, but it's never going to be 0. And that actually makes sense because we know that anything we plug into absolute value, we're going to get a positive number. So if we put the absolute value bars around -2, we'd get +2. -1 would get +1, and so on and so forth. So this actually makes sense. So we're using a table to help us graph the given function. So let's look at another one. This one's actually sort of actual situation, because we're defining our domain as hours and our range as cost. That's pretty much all the information we're given. So maybe it's we're paying a mechanic or something, or we're paying for some sort of service, maybe renting a car. So we don't know, but we're actually dealing with an actual situation here, so we can construct our graph as such, and I'll show you how to do that in a second. So let's say the domain, the number of hours, is given by 0, 1, 2, 3, and 4. And our cost is going to be 25, 35, 45, 55, and 65. Okay, now in this situation, we can actually make a few assumptions, because this is indeed, we're talking about an actual quantity here. We're talking about hours and we're talking about cost. One thing we know about hours is that we can't have a negative number of hours. It can only be positive. You can't work a negative amount of hours. You can't be charged for a negative amount of hours for something. Just like you can't pay a negative cost. You can't be charged for a negative cost. So this is actually, all of our points are going to be contained in quadrant 1. So we can just draw this part of our function, or excuse me, our graph. All of our function is going to be contained in this part of the graph. So we can actually get a better idea of the scale of the graph. So this is our f of x axis. This is our x axis. And we're going to use this table of values to construct our function. This actually looks like we're being charged a flat rate of $25, and it looks like an additional $10 per hour. We've seen a few of these functions and we've dealt with them, so this isn't anything new to us. So let's go ahead and plot a few points. So at 0, at x equals 0, our function equals 25. And before we do that, we need to scale our function here. So we have 40, 50, 60, 70. That's appropriate because the actual function values are pretty large. So we'll do that accordingly. So we have 0 and 25, which is right here. So we have, we have a point right here. At x equals 1, after 1 hour, we're at 35. So we have a point right here. And we need to label our x values as well. Okay, so after 2 hours, we're at 45. At x equals 3, our function is at 55. And at x equals 4, our function is at 65. So somewhere right about there. Okay, so we generally have an increasing linear equation here. So all we need to do now is connect these dots. And I'm sorry this isn't very a straight line, but we'll just assume that these dots are all contained in this line right here. Okay, so this is going to go in the infinitely in the positive direction for both the x and the f of x axis. It's never going to go in the negative direction for either one, so we can just draw it like so. All right, so we're seeing the usefulness of actually converting our function into a table of values before we go about graphing, because doing so we can actually pick out a few points and we can plot them on the graph, and all we have left to do is just connect them with a line. So let's go ahead and do one more. Let's squeeze in one more down here. Let's take a look at the table of values of f of x and x. Our domain is defined as 5, 3, minus 1, 1, and 4. Our range is defined as 3, minus 3, minus 2, minus 1, and 1. So let's go ahead and see if we can graph this thing. Let me get a little bit of room here. Delete this. Okay. So let's go ahead and graph this thing. We're just doing a quick rough sketch. We don't want to spend a whole lot of time on it right now. We can better our sketching skills in the near future, but right now we just want to get a good idea of how using a given table for a function can help us graph the function, and that's what we ultimately want to do. So let's go ahead and plot a few points. We have 5 and 3, which is 1, 2, 3, 4, 5, 1, 2, 3. So we have a point right here. 3 and minus 3 is our next point, which would be down here. Minus 1 and minus 2 is right here. Positive 1 and minus 1 is right here. And 4, 1, 2, 3, 4, and 1 is right here. Okay, so we simply connect these lines, or use a line to connect these dots as straight as we can. Right here. Just connecting the dots. And we're going to assume that this function is indeed continuous and goes infinitely in both directions. So this is a funky looking function right here. It's actually not linear. Well, it's a function, but it's nonlinear. It's a nonlinear equation, or a nonlinear function. So this could be describing some real-world phenomenon, whether it be, a budget, or this would actually be a very bad-looking budget. It could be a profit margin. It could be describing a lot of things, but the most important thing is we're actually working with a table of values, and we're using those to pick out points to help us graph the function on the coordinate plane. So we'll look at a few more of these in the next section. I'll see you soon.